also bring greetings from Jack and Esri and our Redlands office. I was here past few weeks in New Delhi because we are expanding our R&D center focused on GeoAI. And I think a person on my team, Rohit, will be coming here and talking tomorrow. Today what I'm going to talk about is edge computing and its application in GeoAI. Over the past 3 decades, if you look at it, technology has always impacted what we do in GIS. GIS doesn't exist all by itself, but it's a combination of GIS, technology, and a problem to solve with a goal to have an outcome. And you can think of it as every 5 to 8 years, you sort of like have to rethink, not to expire what has happened in the past, but to bring in some new workflows, some new architectures, some new methodologies. So that's why the focus on edge computing here. If I go back to, let's say, 1991, 92, 93, that was when personalized GIS that was made simple came about. Products like ArcView came about, and that was like in your desktop, you want an interactive user experience to get your personal work done. It wasn't the way it used to be done before, which was command line interfaces. And then the internet came about, and it was like, how can you generate maps for a massive audience? Internet map servers came about. And then moving on, it was like mobile, cloud, and so on, right? So all of these technologies had relevance. Doesn't mean that you don't use desktops anymore. Doesn't mean that you don't use mobile devices anymore. Of course, you're going to use the cloud also. So take that within the context of this conversation today. When I talk about edge computing, it doesn't negate whatever has come about so far. Everything that we do back at Esri has to have a larger vision before we build it into a product. And usually it's a decade or more. Sometimes you can see that far, sometimes you can't see that far. But one of the things that we've been able to see pretty clearly is the general trend of digital transformation. It's very loosely used very often, but I want to make it a little more precise in the meaning that I think applies to GIS. So you think of digital transformation, try to break it down into 3 phases. The first phase is the digital twin. By digital twin, what I mean is whatever is there in the physical world that's out there, try to digitize that and bring it into the system in every manner possible. But that what I mean is it's not just the parcel data or the street networks and so on. It's also every observation that's made there. Observations from sensors, for example. Bring that all into the system. So now what you have is a full representation of the physical world that's outside. That's the first phase, okay? And as you do that, all of this data may not be in exactly one database. It might be separated in the most appropriate manner possible. The second phase is to do with how can you do some analysis on this. It's not just about visualization, because that was possible in the first phase. When you bring in a digital twin, of course you want to visualize, and you made that possible. In the second phase, you run some analysis. You do some findings. You do some predictions. You try to find out what can you do to make things better, or why things happen the way they happened. You want to do a retrospective. So all of those are possible in the second phase. That's sort of like spatial analysis to the extreme that you want to take. And then the third phase is trying to bring a loop back. Okay, how can you bring benefit to this at massive scale? And the benefit to that is through ways that you can try to impact the external system through a digital system. So that's where things like GeoAI come in, because there's the human in the mix. The human came into the mix to set some methodologies, but it's sort of like automated in how it goes about and impacts, right? So those are the 3 phases. But there's one problem. And the problem is today's digital twin is trying to get created in the cloud in a centralized manner, okay? If you just look at the globe, it's a vast area, right? Now we're taking all of this and putting it in a centralized way. Now when we put it in a centralized way, one of the challenges is the amount and volume of things that you have, you try to sort of like aggregate to a meaningful thing because you're trying to centralize everything. But we need to go back to the third phase, right? Which is impacting at the highest scale of accuracy so that you're precise. So that's where edge computing comes in, which is don't move everything and anything and every problem to a centralized way. A decentralized mechanism makes a lot of sense in some of these cases like we'll see today. So that's the motive for digital transformation, achieving phase 3, and being able to bring edge computing into the mix. Now, when you hear about edge computing, you'll very often hear about such things, okay? We have to introduce edge computing because there's too much of latency in the response times. Things that go up to some distant cloud kind of atmosphere versus something locally. Or bandwidth. There's a lot of data that's getting collected and it can't be all sent to one place, so you just throw out the irrelevant parts. Or connectivity, or device battery life. Connectivity in the sense that, oh, you're not always connected, so can you do something locally without being able to connect? And then, of course, there's privacy, governance, security, all the things that we talk about very often nowadays, okay? And then, of course, offloading from the cloud itself. There's only so much that the cloud can do. It's not like infinite resources everywhere, right? But the most important thing to keep in mind, okay, is what's the value, which is making decisions at the edge. In the old days, if you take organizations, everything had to go to the top. Very hierarchical structures, right? You have, you have someone at the top who runs the company or the organization, like the chief something. And then you come down multiple layers of management, and then you have people at the field who get the real job done. I think those days are gone, okay? You can't have such, I would say, old ways of doing things. There are new ways of doing things. The phones have become smarter, which means you have so much of information at your fingertips, right? So you can make much more decisions. It's not just the paper flow that's going up and down. It's actually digitized workflows that are changing. So to that regard, what I'd say is we want to make decisions at the edge, which is, in the case that you talked about, Deepak, earlier, it's empowering the farmer. It's not like the farmer has to go to an office and get all of this information after waiting in line or submitting an application and waiting for another week to get that information. Just empower them on the field because they get the job done, right? So that's really the motivation. And so if you take all the things that we're talking about, we're just talking about location intelligence, okay? How can you bring location to make the right decision? And in that, what I would say is this is just defining what I just said, which is empowering those on the edge of an organization. When I use the term organization, we have all kinds of organizations, right? You talked about agricultural organizations where the farmer is at the edge, where people are most likely to interact with the assets. The assets are the crops, right? And its clients, which are the consumers or which are in this case the farmers themselves, with information and data that accelerates and strengthens the decision making. So that's really the motive for edge computing coming in. Now this is just to validate the claim that it is absolutely essential, right? We talk about terabytes very often today as large volumes of data. But take 1,000 of them, it becomes a petabyte. You take 1,000 of the petabytes, it becomes an exabyte. Take 1,000 of that, it becomes a zettabyte, okay? Quite a few zeros. I'm not going to count now, but this is just for reference because I'll get it wrong all the time, right? So this is how much of data, 850 zettabytes. This is generated data, okay? This is not stored data that I'm talking about. This is how much of data is generated by people, machines, and things on the network edge. But how much can a global data center traffic of all the data centers in the world, they can only reach this much in that year. So what is happening to all this data is just getting lost, right? You have sensors. When you purchase the sensor, the claim is it can sense every 5 seconds and it can sense a pulse. But if that's the volume in which you consumed, you have to have a lot of storage, bandwidth, and so on. So today's system is such that it cannot handle that. So your sensors, just like your smartphones, are super high powered, but we can't use it. It's not useful. So it's very difficult to build reactive real-time systems because of that challenge. So that's something that we need to solve. Another thing is just the number of things that are going to be connected that are internet enabled, right? It's a pretty large number, 50 billion. It's a lot more than the people who live, right? Now, just as an anecdotal example, when the 787 Boeing was created, it was like very modern for its time. It had lots of onboard computers. It was generating 5 gigabytes per second, which was pretty significant volume of data. Today's cars generate 1 gigabyte by second. Okay. I'm not talking about level 3 and level 4 cars and autonomous cars and so on. I'm just talking about semi-autonomous safety systems, cars which have built-in safety and so on, auto braking and things like that. That's a lot of data just for some comparisons. So what used to be an amazing amount of data at one time, where you can have a plane load or a ship load or a plane, whatever load of computers, now just gets into a simple car. And a car is an automobile, it's not a computer system, right? Yeah, so this is just a little more of the same point, re-emphasizing. So, yeah, this is basically a study that found that if you had 30,000 sensors in an oil rig, less than 1% of the data is currently used to make the decisions. Okay, less than 1%. So that's significant. So why were these sensors ordered that could generate this much of volume of data, and then you finally don't use it? It's not efficient. It's not useful. Then the other thing is, okay, how is that going to be used? Gartner, they try to predict technology and how to use it and so on. It's an organization. They estimate that by 2025, 75% of data will be processed outside the traditional data center or the cloud that we know of today. So how do we prepare for such a system? The key thing is you have to be able to distribute software at a massive scale. If you take cell phones became very productive for all of us. They became very useful mainly because the distribution of apps through the App Store became like a non-event, you can say. There was a time when if you had to use a cell phone, whether it was a hit or miss, how do you get the apps, right? Today we just take it for granted. It just gets automatically updated, and it's doing that across billions of devices today, right? So the same thing needs to happen in order for this kind of an architecture to work, that the enterprise itself is expanding. It's expanding, it's growing in its reach, and it's going to the edge. So that's how we look at it in terms of how to achieve this vision going into the future. Now, another way to visualize this whole problem is there's a whole lot of data that's getting collected. It's coming from satellite imagery. It's coming from drone imagery. And I heard that you had a visit and you had a very impressive drone demo too, right? So you get the point on how useful it is. And you have massive volumes, billions of IoT sensors all feeding into the cloud today, okay? All of these. They're just layers of information to help you make the decision. But it's not some omnipresent cloud that is out there. It's just a physical data center that's down here, okay? That's really what it is. When we talk about the cloud, we somehow, when we program, we think that, oh, it's there everywhere. I've got infinite resources. It's elastic. And it's just there. It's like as if it's floating around in this room, right? That's how we think of it. But in reality, it's grounded. It's grounded in reality in the sense that it's in one place, in one location. And there are many such locations. So we talk about multiple regions of the cloud system based on the provider and so on, providing value. But there's only so many places in the world that you can have such data centers, right? So if you look into the future, this is not to scale, of course. So if you expand a smart city, okay, just think that this is a smart city. It's got like whatever, 20 square kilometer or 200 square kilometer, depending on the size of the city. It's still a tiny piece on the earth, okay? I've just expanded just to make the point come across. You have lots of sensors. There's a massive area to cover, okay? That's the surface of the earth in which all these cities could exist. all these pieces of land that have value, that need to be sensed, exist. And if you take all these kinds of inputs, the city cares about it coming to one place to make the decision. Okay. I want the satellite imagery at a very high resolution only for this region. Okay. Or I want to fly my drones and I want to get it right away just for this reason. One is to do with rights management, privacy, the accuracy, costs, and all of those. Another is the practicality of where does it make sense to have this data because you're making the decision here. And you want to overlay that along with all the IoT sensors that exist. So in a lot of places you have CCTV devices. You also have many other sensor devices, what's the air particulate matter and all of those that are all there within the area. So you want to bring it all down to one place and see how you can make sense out of it. The next thing I want to talk about is when we talk about edge computing, you'll hear fog computing, you'll hear many terms. It's fine, all of those are, perfectly make sense, but for the sake of this conversation, because we don't have endless time, right? How can we partition this? The way I'd like to partition is there are edge devices that are getting more and more powerful. An example is you have AI-enabled chips on smartphones. Of course, they are massive compute on your phones. Then there are many other devices that can also compute, like with Raspberry Pi or some chipsets like that, to make decisions. So I'll just put them in a category of edge devices, okay? Because they exist first as devices that have compute in them, as opposed to existing as compute made as a large device, okay? So that's why the differentiation here. So let's keep that aside. I won't have much of a conversation about this because that's a whole different topic all by itself. Then there are edge servers. You can think of the best example of edge servers is there's Industrial 4.0, which is underway. And think of that as it is an automation of your shop floor or your assembly line and so on. So in order to enable that, you have massive systems that are all interconnected. They're complex systems. Humans don't interfere with the functioning of the system unless something really goes wrong. The day-to-day activities are just taken care of in an automated manner. You can think of them as services provided between these servers to get the job done. And they could be stationary, they could be mobile, they could be in any way that you want, okay? There's no human interaction, that's the key point here. Then there are what I call edge portals. Edge portals are basically what we have today in the cloud coming down to the edge and being meaningful, so you don't need to retrain anyone, okay? So a key aspect of bringing any new technology and making it acceptable is reduce the barrier for acceptance. And very often reducing the barrier of acceptance means minimal or no retraining required. Set the expectations to what it was and it'll be quickly accepted. Because as humans, we resist change, right? We are challenged by change as much as we ask for change. So if you look at this aspect, it's whatever you have in the cloud, personalize it for the edge. So that means it has all the mobile devices and mobile app connectivity. It has all the web applications and the web interfaces and everything else. And it's built for humans and for machines. So it's just the same thing coming down. One example is, let's say you're fighting a fire, or you have a massive forest fire, or you have some other emergency situation. You want to consolidate all of that in one place and provide it in that place as you go through that activity over, let's say, a few days or a few weeks. So how can you quickly make that? Because it could be disconnected at times, it could be partially connected, and you might need to do things quickly, like we did today. You gave me your USB drive because you wanted to transfer some data into this. I actually didn't get on the Wi-Fi network, provide the right password, copy it to Google or some cloud drive, and then you having an account in that place and bringing it down. It was much easier just to transfer, right? So there are many things that happen in such a system where you're trying to localize how you get things done. Because not everything can become global. As we try to do everything global, it's the sum total of everything. The sum total of everything is usually a weak thing. It's nice in agreement, but in terms of accuracy and the flexibility, it becomes weak. Yeah.
Now on the edge portal, well, on the front end you're calling it an edge portal. The portals probably are being serviced by cloud again.
Not necessarily. That's my point. So today's portal, if you use the URL, it's going to some cloud, let's say. Okay. In this case, it could be going to a local edge compute that the city has. So for example, the city of LA today has its own internal portal, enterprise portal, and it has a cloud. So for external entities, partners, contractors, and so on, things that are not sensitive, so to say, they would use the cloud. Okay. There's only so much of stuff that will go there. But for certain other ways of managing things, they have their own portal. And that portal itself today, of course, it's in the IT department of the city, you could say. But tomorrow, it could be distributed across the city so that if something catastrophic happens, you don't bring the whole system down. You can still make you can still execute what you need to. Now, I want to go back and re-emphasize the point, which is when you talk about such a system, you don't need to eliminate what you already have. Okay? You build on top of that. But you need to recognize what is one good for versus the other. Now, this probably has a little bit too much of detail, but I want to make you think about this. If you're thinking about the big picture, okay, a centralized cloud is extremely good. If you want to have a local regional picture, it's like, when do you keep your photos on your phone? When do you upload it to the cloud? When you want to share with your group of friends or family, right? Whereas if you want to study something locally, you just keep it on your phone. Historical and batch analysis. So that means accumulating data over time, over history, archiving them and so on, and then doing batch analysis, which is find the right time when you're going to execute this. Once the volume of data has become this large, you do some analysis, or periodically, every Saturday night, it takes 6 hours, so run the batch analysis because someone who comes in on Monday can see the results. Those kinds of things, centralized cloud is excellent. Specialized, focused, real-time analysis. As soon as you get the data, you're looking for an anomaly, okay? You're looking for some anomaly where maybe there's a leak in a place and a sensor in and around that place, a series of them are now detecting some particulate matter level has gone up, okay? You want to detect that, you don't want to wait for the Saturday to run this batch analysis. As soon as you receive it, you want the alarm to be set on. The alarm could be one sensor, may not be enough, 5 sensors. You might set the alarm for 5 regional sensors all triggered at the same time with abnormal readings. So that causes an alarm, okay? So those kinds of things are good at the edge. Archiving, absolutely. The cloud is elastic, you pay as you go, you have much more larger volumes. It's more to do with recurring expenses versus capital expenses. There are different ways that you use the system, right? As opposed to, in the short term, you filter the data before streaming to the cloud, which is, if a sensor is recording something and it's telling you the same thing over and over again, you just do a check at the edge and you ignore it. There's no reason to send it to the cloud, because most sensors are going to send you the same reading over and over again. If there's some change, if there's some delta, and you can set the parameters for how much of tolerance you would have, only then send it to the cloud. But when you're sensing it locally and you're doing the analysis, doing it at the highest accuracy possible, because that means you can be so much more confident about the results that you're getting. This is similar, somewhat related to batch analysis, but here it's talking about the volume of the data that's used. When I use the term massive analysis, and the scope is also wide, which is a larger set of people are impacted. Let's say the decision makers at the state level or the central government level and so on. It probably makes sense to use it at a centralized cloud level, okay? Because you want to aggregate data and you want to apply it in a common way across the board. Whereas at the local level, precision analysis, limited scope. Like for example, you might say that some cities or some villages or some states have more accurate data collection procedures because they invested much earlier. Others haven't caught up. So do others pay the price for it, or does the one who invested pay the price for that? Neither one should. They should get the best results possible. So how can you do precision analysis within limited scope to the best ability of each place? And then, of course, there are things like data is massive. You want to consolidate them. Of course, it makes sense. It's constrained by collection region. Like we talked about, what kind of data or the privacy and other issues related to that. So, for example, if you collect data, you want to anonymize the data. But when you do the analysis, you might not want to anonymize. But the law might be that if you try to bring it to a central place, you have to share for privacy or other concerns some of the attributes of that data set. So you don't want to lose that too early. Maybe you lose that here, but you may not lose it there. And then you have cases like, okay, your edge is usually fixed computing needs, at least the immediate future. Probably a little bit into a distant future, it might get flexible, but right now it's not. So if your needs fluctuate, the cloud makes a lot of sense. And then, of course, there are things like if you want to train models and do batch inferencing, which is when you train models, it's not ad hoc. It's not based on, oh, today I received lots of training data. Tomorrow I don't receive, so immediately I have to do. No. Usually all of these things happen at a very set interval because you want to follow them some QA and QC practices that are already in place. As opposed to instant inferencing at the edge. So if you have a model and you want to find the answer, you might do at the edge. Similarly, selective model training, which is I have this data at the edge, it's too large, or I cannot move it to a central place, but I want to use it for training. I don't want to introduce bias, but it's useful data that I can have for training. So those kinds of things can happen at the edge. And then this is great for thin, lightweight, always connected clients, because to use the cloud, you have to be always connected. Whereas if it's disconnected or you have limited connectivity use cases, you create an edge scenario where you can always have it available. And the last one, I think, is the most important one, which is if you can afford to defer the attention that you give to the answer, this is great. If you want it instantly, as it happens, you're going to react to it. Again, it's to do the decision making at the edge, right? How quickly do you want to make that decision will help you decide which one is the right place. So I'm going to jump into, now this is all like very nice and visionary, you might think, but how does it practically apply to technology? So one of the things that we do is try to take what's emerging, try to see what brings meaning into the software architecture and what we build, and is it palatable and usable by users? So that's sort of like the loop back for us internally. And as we do this, not to negate everything that's out there, because not everyone will care about edge computing in the next few years. Some may not even care into the distant future, right? They want to continue doing what they're doing. So how can you accommodate both kinds of systems? How many of you are familiar with terms like microservices? Okay, good. So I don't think anyone knows, but I will explain, okay? So in previous years, a lot of software systems that were built, today we can use the term monolithic, which is it has everything in there that you want. Every piece of functionality is built in. And it's all in there. So you go to one piece of software and it gives you everything that you want. And that's good. It's good because you don't need to go to different pieces of software. It's good because it's all self-contained. And as someone who's installing and using the software, it makes sense. It's very much a desktop-driven philosophy, okay? Because that's how desktops work. You put everything in there and it just works, and that's it. But what happened was that as we started building distributed systems that are running on servers, systems that have to be updated, systems that are used for mission-critical, business-critical systems, and so on, you run many servers. Now just think about it, you've just built a monolithic server, it has to be highly scalable. You make a tiny update, okay? You have to update all of these systems, with massive pieces of software that are monolithic. Okay, so it takes a lot of time and effort. If let's say you have 2 million lines of code functionality, and you just change one line, now you have to go and test all of them because you actually don't know what changed, and you can't risk not testing all of them because it's a critical system. And then the other thing is, if you have to scale this, you're scaling the whole thing. Whereas all you might care about is image processing, or you might care about geocoding, or you might care about one analysis tool, which is what many people use. You don't care about the full visualization system. You don't care about all the databases it can connect to and so on. So for building large distributed systems, going from, you can say, macro service or a service of services, microservices, a term was invented, which is break it down into small parts, because when you need to scale, you can take the small parts and scale them. So if you want a certain set of functionality to scale, then you scale only that. If you want to fix a bug in a certain functionality, you fix only that. So you don't need to spend a whole lot of time going through change. So you can think of it as today's change is expected, anticipated, and how do you account for it? Okay. It's like if you have a problem in your car, you don't go and replace the full car, you replace just the part of it. And someone gave you confidence that that part is all you need to replace. If the light bulb is fused, you just change the light bulb, you don't go and change the car. Okay. And how to build such systems that can be partitioned that way in a meaningful way. You know, the lighting system is different from the transmission system, is different from another system. So you have to re-architect. You can't just like ad hoc try to build every tiny piece like this. You know, are you going to change the fuse wire in the bulb? No, because you're going to make it meaningful that someone can actually pull it out and put it in. An average person can do that, and so on, right? So how to build software systems that can also be similar? That's the goal of microservices. The term containerization is used. How many of you know the term virtualization or virtual machines or VM? Any of you? Okay, some of you know that, right? So most enterprise systems are virtualized because you can reproduce exactly what you want. The only thing is, with that technology, the operating system itself that it's running on was duplicated over and over again within each VM. That was an overhead. So with containers, that overhead is taken away. So it's sort of like an internal detail. It's a much more optimized way of doing it. And the last one, orchestrated architecture, is, like I was saying, earlier systems were all desktop driven. From desktops, it went to servers, but they were still like each individual system that is running, some IT administrator or DevOps person has to come and make sure that these 100 systems that it runs on all should look exactly the same. So they'll write lots of tools to make sure that machine 1 is the same as machine 55 is the same as machine 77, kind of, right? That's a lot of effort. What you're trying to do is you're trying to orchestrate a system where everything looks like the same. So with this new technology called orchestration, what you do is you define the end state of the system. Okay? You define what you like to see, the full system. What should be running on 20 machines, what should be running on 50 machines. And then this technology will ensure that it's constantly checking whether the end system is what is the current system. Okay? That's its job. So that's what is meant by that technology. Now let's zoom out again. Okay. We all agree technologies are advancing rapidly, right? So if you don't bring in something and benefit from that soon enough, it's going to become old and you're going to get outdated in how you can accommodate. But at the same time, it's not a world where you can have multiple things running in parallel, because that takes resources also. So what's really happening out in the world? You would have heard of some of these terms. Private cloud, okay, which is something like a public cloud, like AWS, GCP, Google Cloud, or Azure, are all examples of public cloud. Now, some of those technologies, plus other additional vendors, created private cloud, which is whatever is out there in the cloud, can I have it within my premise? And it's really providing some of those same features and capabilities on premises. So these have existed for a while now, both of these. Now hybrid cloud is, I don't choose just one. I would like to have the best of a couple of them. But typically the couple of them, when we use the term hybrid, was public, I choose one public, and then a private. A lot of organizations exist that way. I have a firewall. Within the firewall, in the secrecy of the firewall and the, you can say, the security within, I will run systems in my private cloud. But there are things that I have to share with citizens, with the residents, with other contractors, with other entities outside the organization, and for that public cloud was used. When both of these were used in unison, in a very systematic manner, it was called a hybrid cloud. Now multi-cloud is basically, to get the job done, I might use the best of everything in a full workflow itself. Okay, that's the term multi-cloud. So for example, you build a large SaaS system like ArcGIS Online is. In order for it to store data, a certain cloud might be good. In order for it to process imagery, another cloud might be good. In order to present user experiences, another one. But to the end user, it doesn't matter. The end user, you're just getting your job done. But behind, that system might be running across multiple clouds. And then edge cloud is something that I just introduced for this slide, that just think of it along those lines. Doesn't mean any of this is going to go away. They just get enhanced at the edge. So if you ask a cloud provider, is it the end of the cloud because edge is coming about? The cloud provider ideally would say, no, I just expanded the reach of the cloud into the edge. Okay. But at the same time, if you take data centers that existed before this, okay, large telecom companies and others, they already had edge compute, because to run networks, you have to be at the edge. You have to have a lot of compute at the edge. So they already had that. So we expect that they will also be in that space of edge cloud, because that's something that they didn't get into this, okay, late to the game, whatever you might say. But certainly that's something that you can expect to see. I'll skip through this. It's just a definition in words, pretty much what I said. But a key thing that you should probably understand is earlier network functions, okay, were not virtualizable. That means you cannot put some device that can run software, now it can, that can actually manipulate the full network itself. So it's not hardwired, it's soft-wired, you could say. So that is actually creating virtualization of networks itself. And that is driving edge computing faster than it could have otherwise. Then the other thing is software-defined networks. What are trusted networks that you form at the edge? Now you can define that through software. You don't need to play with switches and cables and things like that just because things are changing. No, you set up a generic system, and then through software you infuse all of these things. I'm going to this level of depth just to share the fact that GIS is not all about the practice. It's often about the acceptance of technology that is relevant. It's not every technology that's relevant, but the end user doesn't need to care. That is, I think, primary. The end user should never be impacted by technology changes other than seeing the positive outcomes of that. Okay. They shouldn't have to see the friction of what it took behind the scenes. But behind the scenes, you know, as implementers, we might see friction. But to the end user, it shouldn't matter. So if you take today's ArcGIS Enterprise, I just took it again as an example to illustrate that point. Like I said, the current system, that's going to go on for many years. We have to introduce a new system that is built a certain way, that can expand a certain way in terms of the scalability aspects, the maintainability, and so on. But to the end user, it should be exactly the same. So today we have a system of engagement, which is your interaction with the apps, with the website, users, the roles that you play, the portal that you know of, and so on, right? That is exactly the same, no change there. Today we have the system of record, which is where do you store all your data, the data that you care about, your observations, your asset data, all of that, you put it in your system of record. Then you have the system of insights, where you run all your models and you find your answers. Those are all exactly the same. So at a certain level of abstraction, this is the promise to the end user. They actually don't know. Are they connecting to an edge compute-based system? Are they connecting to a cloud-based system? Or are they just working, like they always used to without knowing any of these things? It's exactly the same. It'll have all of this functionality or some of this. Okay. A big difference is what is actually going to be behind the scenes. That is what is changing. So there's a technology called Kubernetes that is getting very popular. You can think of it as the cloud operating system. If you have to dumb it down, what exactly is it? We had Windows, we had Linux. Okay, most popular ones. Earlier there was Unix, there were many others also. They are all operating systems that take hardware and give you the ability to run software. Those are built for single unit systems. In other words, one piece equipment. Now Kubernetes is built for distributed systems. So you can think of that as the operating system of distributed systems, especially that are cloud-like designed. Okay. And when we do that, what has changed since the old times is it's not just CPU based, but also GPU. GPU is just another kind of computing capability that can be massively parallelized. In AI, a lot of that is required. So how can such systems come into it? And then of course the data stores are just the same as before. Right? This is like an architecture diagram. You have the traditional deployment, bare bones hardware. We call it running on the metal, which is running on the machine. We talked about virtualized, where like you can see, the operating system is duplicated in every VM that you run. As you see here, there's only one operating system. It's running Docker, which is the technology that's used in the space that's pretty popular. Just like VMware's virtual machine are popular here. And then this orchestration is through Kubernetes, where you can have multiple Docker containers doing different things and being able to scale. So this is the sort of like the progression. It's the progression, but it also means we don't give up on these things because they make a lot of sense in the places where they're using it already. Some of the reasons why people choose this. We need more control, don't want to have vendor or cloud lock-ins, portability, all of those aspects, right? Now, one of the reasons for using Kubernetes is they have technology called Kube Edge, which is if you build it for this, you can run it at the edge, and that's the operating system at the edge. There's no difference there. So designing systems for this will help us get to the edge also. I'm going to take a simple example, like a GeoAI workflow with imagery. I think Rohit might show you a few examples of this tomorrow. But let's say in the cloud, you have the full end-to-end workflow. How do you access the imagery? How do you prepare the imagery? How do you label the imagery? Let's say you're trying to train something. Use it for model training. And then you deploy it into production. You consume these models. You call inferencing on that. And you might do it at scale, like batch inferencing. Now, this whole system might be running in the cloud. You don't care at that point whether someone is using lots of data labeling, someone's doing lots of this. Not many are coming and like running it at scale, or not many are training. It gets trained every day or every month, you don't care. But the full system is available at your fingertips for use. Now, what might happen is in the edge, firstly, the edge can be mobile or stationary. You might run just small parts of it. Okay, some parts of it that are meaningful. That's like saying that if I want to do batch inferencing, I go to the cloud. If I want to do some inferencing at the edge, which is as the data comes in, I want to find out something like a CCTV feed that is going to give you at, let's say, 30 frames per second. And you want to actually do some analysis at 30 frames per second. You'll have to run it at the edge. You're not going to stream 30 frames per second video upstream, right? Same thing with the sensors. If your sensor is able to detect every so often and you want to find the anomaly, or you want to find some other analysis based on that, over the last 1 hour, what really happened, and I want to get the reading so often, you don't like keep sending it to the cloud and then processing there, right? So all of these are possible. You can pick and choose which parts. So this is what is the value of a microservice, okay? Some of these are the only things that go here, not all of these like a monolithic system. Now, obviously, we don't control the cloud. Esri as a company, we are a GIS company. Okay. We see what is happening out there. What are the trends that are going on? What are other companies that define some of these spaces doing? So I just picked a few examples. So Amazon has this AWS Snowball Edge. It's a device, it's ruggedized, you bring it to the edge, you deploy it, use it for that purpose. There's Azure DataBox Edge, a family of devices that serves the same purpose. Very often they have inbuilt GPUs for high performance compute and so on. So you can also think of it as this is HPC at the edge that's happening now. And then there's NVIDIA, very popular in the GPU space. AI is often done on such systems. They actually have an offering called EGX, which is their edge compute. And you'll notice the similarity in all of these things is there's Kubernetes in the middle of it. That cloud OS technology, the edge OS, I would say, also trying to bring it in. And then there's Google, where it doesn't matter. It's multi-cloud ready. They have provide the tooling, and you can run it in any of these clouds. It doesn't need to be Google's cloud necessarily. So such systems are being built. The nicest diagram I have trying to illustrate this point is what Azure introduced recently called Azure Arc. It's a centralized management system. You can control any cloud with that. You can operate any cloud. And it can be on premises, running on any hardware. It can be on the edge too. It's providing this management, all the data and the services that are out there. So it's really us coming into this world where you choose what is best for you, and very often you'll choose multiple of these to get the job done. These are some examples of I'm not sure, the video is not playing, but I will explain what these are. These are all examples of things that are ideal for running on the edge. This is, for example, all the sensors in that bus trying to detect what is around it and using all of those inputs for many factors, safety being one of them, traffic, changing the lights, seeing what is happening in different places. All of those are examples. What I had here was detection of objects, people around, and then updating a system of record directly with that. Okay, I think the animation is missing, but this is also similar. The point here is that AI and object detection and all of those at the edge become relevant if you can make it meaningful into everyday workflows. So in this thing, the animation that you would have seen is, okay, click on something, you see what is happening. That sort of visualization in an operations dashboard like environment. But what this would have shown, if animated, was in real time, it was detecting all of these things. This whole thing was in real time. So that's the difference. So to the end user, it doesn't make any difference. The same URL they go to, it's the same web application they interact with. It's just that it's not like an hour-old piece of information or a week-old piece of information. It's live, current information. You can expect that GeoAI is going to disrupt all of these, and edge computing is sort of like right in the middle of trying to solve many of these problems. When we talk about intelligence, you can see that we have device intelligence, we have cloud intelligence at the extremes today. Okay? What we'll see is filling the gap. And when we fill the gap, it's not a either or, it's an and. You'll use multiple of these systems to get the job done, like you see here with these examples. So with that, I will stop now, and maybe, I don't know if there's time for questions, or I'll be around and we can, a few questions, or I can be here and you can come by and ask me any questions.
An operating system, kind of distributed systems, whether it's phones.
Right.
If you see any operating system that is coming up today, multiple processing is as such happening, parallel processing takes place, and multiple functionalities that you are doing based on the processing that you have. So don't you think the existing operating systems also are similar to Kubernetes only? So how this edge operating system and the strength that is being given, how have you introduced that into this?
Okay, great question. First disclaimer, Kubernetes is not something that Esri had a part of. It was originally created at Google and it's open sourced. So to your question, at first we had single threaded processes that on a chip, a CPU, it uses all the cycles to get that executed. Then we wanted interactive systems or parallel systems. So there were technologies like hyperthreading and so on that ran through. Then meanwhile, also in parallel came about multiple CPUs on a single motherboard. So you could have multiple processes running and taking care of all this. But all of these systems are actually in one box. Okay. So we couldn't scale the box. If you scale the box, then we'll end up with mainframes, right? We know all the challenges of mainframes. Only a few can have, it's not democracy at that point, right? Only a few restricted places can have it, right? So what happened was we started connecting many of these systems in server rooms, data centers, and then parallelizing them across multiple nodes. We call it distributed computing because it's distributed. Now when we did that, the operating systems were still running on a unit level of the CPU. They weren't running at the global level of the distribution. So what this tries to do is it understands the full fabric. It's like a network fabric. It understands that and it tries to apply whatever you need across the fabric. Like I want 5 of this, I want 10 of this, I want 2 of this. That might be now, but if I get load, this can go up to 15, this can go up to 25, this cannot go up. All of those rules you can set up in this. That's fundamentally what it's trying to do.